Thanks. So the title is Comparing the Decoherence Effects Due to Black Holes versus Ordinary Matter, based on this paper with Huang. So recently, a thought experiment was discussed in the literature, which involves a quantum system decohering due to a black hole. And it was suggested that this effect might be unique to black holes or be of fundamental importance for their quantum description. We also expect that black holes should be described from the outside by an ordinary quantum system. So in this work, we replaced the black hole in the thought experiment by an ordinary quantum system and found the same qualitative effect. The idea, as I'll discuss, is to analyze the problem in terms of an effective theory that applies equally well for the black hole and ordinary matter case. So let me review the thought experiment. There is an experimenter, Alice, who prepares a superposition of an electric dipole pointing in two opposite directions. She holds the superposition for a long proper time t and then adiabatically turns off the dipole. And Alice's environment consists of a second quantum system, what we call the black quantum system, which could either be an ordinary matter system or a black hole. And we're interested in the limit where her distance from the black quantum system, b, is much larger than its size, r, but much less than the time of the experiment. And these previous papers show that a black hole will decohere her superposition at a constant rate. OK, so now we want to write down an effective theory for the interaction between Alice's dipole and the black quantum system. The dipole is sourcing fields which have a wavelength much larger than the size of the black quantum system, so we can approximate it as a point particle in flat space with some operators living on its world line. And the leading interaction with her dipole is given by is coming from the electric dipole of the black quantum system, given by this action. And now when we compute the time evolution of Alice's density matrix under this interaction, we get a constant decoherence rate proportional to the time integral of the PB two-point function. So in this framework, the decoherence is arising from thermal or quantum fluctuations of the black quantum system. So now let me say how we relate, how we compute this two-point function for various systems of interest. So one way is to compute the response function, or the retarded Green's function, which is related to the two-point function by the fluctuation dissipation theorem. So for an ordinary matter system, the response function depends on transport coefficients like the conductivity and the viscosity. For black holes, it's given by the Love numbers. So famously, A, the static Love number, is 0 for four-dimensional black holes, but B is generally non-zero and is responsible for the effect in question. And indeed, from a computation of the Love numbers, one can read off the two-point function and reproduce the decoherence rates in these previous papers. OK, so finally, we can estimate the response functions of various ordinary matter systems and use that to get the decoherence effects that they would produce. So for example, if we have a conductor with some resistivity rho, then we find that this would have a comparable decoherence effect to a black hole of the same size when rho over r is order e squared, and e is 0.3 in our units. So a sufficiently small conductor of some impure metal will do. And then there is an analogous version of the effect that I didn't discuss, which involves some matter quadrupole superposition sourcing some gravitational fields. And in this case, in the gravitational effect, we find that an ordinary object of the same mass as the black hole would have a larger decoherence effect, typically, while the opposite is true for an object of the same size. And here's a summary that you can read, because I'm probably out of time. Oh. 4, 3, 2, 1. OK.
Question?
Unmute. Just unmute yourself if you have questions.
Yeah. Hey. So thanks for the nice talk. I mean, maybe an alternative way to interpret this is to say that, by the so-called central dogma, black holes are just the same as any other quantum system. And so then Gautam and Wald, collaborator, found that this decoherence effect is an effect of standard quantum systems, and then what they showed is that somehow black holes are able to do that. They're even more of a standard quantum system than we would have otherwise thought.
Even more in what sense?
Well, that they have this decohering effect, right? Maybe from classical GR, it's a bit surprising that a black hole can be decohering, and they explained that it is, just like you would expect.
Yes, yes, yeah, I agree.
Well, you guys were this close to be gonged in here. Okay, this was Anna Biggs. Thank you very much.